start the record on this thing, minimize my control.
Actually, I think I might just send you the pictures of the problems.
Okay, if that's easier, go ahead. You still, yeah, if you type DA, it'll pull up my email address for you.
Where's that?
Well, once you take the picture in your phone and you go to share it,
Okay.
share it to my email address, which begins DAV.
Okay.
And since you did this once before, your phone should have it in memory, so the moment you type the first two letters, it'll pop up my full email address. Let me know when you sent it.
Okay, let's see. Okay. So mail, mail. DAV.
DAVID COWAN 1949 at gmail.com. I can write it out for you if you need me to.
Okay. Okay, I just sent it.
Okay. There it came. Yeah, now the next time you shouldn't have to type the whole address out. Your phone should memorize it. Which page would you like to start on?
The first page. The biggest page.
Okay.
And then 22.
Ooh, what kind of, you have an iPhone?
Yes.
You need to send it as a large image.
Okay.
Okay? Because otherwise I can't read it.
Okay.
And you need to keep the camera as still as possible when you take the picture. The lighting looks fine, but you need to send it as a large image. That happens a lot with people who have Apples. If they send it as a small image, the resolution isn't good enough to read it.
Okay, I just sent it large.
Okay, good. Hasn't come through yet. Well, maybe it'll take a little bit longer for a large image to come through.
Yeah.
There it is. Now watch how much difference it makes in the appearance of it.
Oh, there we go. Okay.
So which number you want to start? 20?
22.
22, okay. Let me first of all read the directions. Sketch the graph as check for, okay. So they want you to graph this 2x. What's the first thing we should do in the bottom?
Write them both out? Or
Factor it.
okay.
Almost always, when you see something that can be factored, you should do it. It's rare that you don't want to factor stuff.
So
how does it factor?
X plus 2x minus 1?
We're doing the bottom. X squared plus x minus 2 factors into x minus 1 and
X plus 2.
Plus 2. Okay? Now that gives us a framework to work with. In other words, the very first thing you want to put on your graph is the vertical asymptotes. Where are they?
They're at 1 and negative 2.
Draw dotted lines. How about a horizontal asymptote?
0, right? Because it's
Correct.
x squared.
Y equals 0. In other words, these asymptotes are always equations of lines. So just saying 0 isn't quite enough. You have to say y equals 0, because otherwise it could be x equals 0. But x equals 0 would be a vertical line. Horizontal line is y equals 0. So now we have an idea on how this thing's going to graph. It's going to graph most likely, we know it's hyperbolic in nature. All of these are. And whenever they're hyperbolic in nature, they almost always do this. And this one, because it has two vertical asymptotes, well, it's got to do something in between here. And they usually take one of two paths. Looks like that, usually. Or it could look perhaps like that. And we're going to have to play around with it to see which one it is. I'm going to leave the blue up there because I'm pretty sure this is my choices. And sometimes you can be in the wrong quadrants. In other words, what I see here is 1, 2, 3, 4, 5, 6. There's actually 6, can't call them quadrants, sections, okay? And usually the hyperbola is in the upper right and the lower left, but I can check really quick how. In other words, maybe it should look like this, where in that quadrant. How can I tell really quick to make sure I've got it right?
You can plug in a number.
What kind of a number? What number?
0?
0 is between the two asymptotes. If we're checking for this red curve right here, then we want to plug in a number greater than 1.
Oh, yeah.
Right?
Yeah.
An x greater than 1 needs to produce a positive answer for this graph to be correct. Well, when I plug in 2, I get 4 over 4. That's a positive number. So I got it right. Okay? I got at least this part of it right.
Okay.
And just by merely checking, I know it's hyperbolic in nature, so I know it's going to go towards that asymptote and towards this asymptote. The only question is, do I have it in the right quadrant, so to speak? Typically, you'll only have 4 quadrants, but in this case, we have 6. Okay, so I got that right. I could check over here, and I could plug in minus 3. Well, what does minus 3 give us? That gives us
6.
Minus 6 over minus 4 times minus 1 gives us minus 3 halves. I got this one right. I'm below the x-axis, which is I need to be. Okay?
Okay.
See how I checked that?
Yes.
I don't want to go so fast that you're not understanding what I'm doing. Okay, so now the only part that's in question is the middle. Do I have the blue part or the red part? Well, what's the difference between the two? The red does what?
It crosses the horizontal line.
Right. And that would mean that there is some value of x where y is 0. So the question is, does this have a solution? If I let that equal to 0, can I solve it? Can I?
Yeah, wait.
Is all you need a rational quotient to be equal to 0 is if its numerator is equal to 0. In other words, for this to be true, 2x must be equal to 0, which means x equal to 0 is an x-intercept. Okay, so I now know that it's no longer the blue line because I know I crossed through the axis, and in fact I crossed through, oops, I crossed through right at that point there where x is equal to 0. So now I can draw my line. It's going to look like that. And also, it's not always true, but I would say most of the time, when you read these final graphs from right to left, and that's how we graphed it, we graphed that first, notice that this approaches that asymptote headed towards positive infinity. Now,
Right.
this comes from the other way. In other words, on the other side of the asymptote, we're coming up from negative infinity. We end up approaching positive infinity as we approach this asymptote on the left, which means we're going to have to come up from negative infinity on the other side of that asymptote.
Okay.
Now, they don't all look like that. It is possible to have something that might look like this, where there would be a vertical asymptote right there, and notice that it approaches positive infinity and comes off of positive infinity on the other side. So it's not a hard and fast rule, but I would say with most everyone you're going to see that's going to be the case.
Okay.
You can almost assume that and then check it. But so we graphed 22. What's next?
24.
Okay. 24 says 5 times x plus 4, and that's factored. I'm not going to distribute that yet. I may not want to distribute that, but I can tell the bottom needs factoring. What's the bottom factor into?
X minus 3, x plus 4.
And usually one of these is always going to be the same as one of the factors in the numerator. Okay? So what now?
Cross out x plus 4. The top one.
What now?
Vertical asymptote at 3.
About a horizontal asymptote?
0. Y equals 0.
Right. Okay, so now we really do have a quadrant grid. You know, this is quadrant 1, 2, 3, 4. Now, what about what I crossed out? X plus 4 on top and x plus 4 on the bottom. Does that show up anywhere in my graph? Or is my graph strictly 5 over x minus 3?
Does that mean there's a
Hole.
hole?
Hole. That's how you generate holes, is by factoring out stuff. The thing is, though, is to figure out what values x cannot be. In other words, if you want to figure out the domain for x, you have to include that original point. In other words, in the original function, x cannot be minus 4. So even though I've modified the function, I still have to carry forth that domain restriction. X also cannot be 3, but we're looking at that by a vertical asymptote. Whereas at minus 4, it doesn't show as a vertical asymptote, it shows just as a hole. Now, if this is typical, then I'm going to have 1 there and 1 there, and I'm going to have a hole right there. And that'll be the graph. Now, like I said, I don't have a real good feel when I look at a function whether I'm in quadrants 1 and 3 or 2 and 4. So let's check. Pick a number. Let's make sure we're in the right quadrant there.
4.
Okay. Anything to the right of 3 is good. So when you pick x equal 4, you get 5, right?
Yes.
So we're above the x-axis, so I'm in the right quadrant. And I could test this one, but I don't need to. Once I've tested this and I know that quadrant 1, in other words, I don't have anything sophisticated there like an x squared. If I had an x squared, then I could be in quadrants 1 and 2 instead of 1 and 3. But as long as it's linear in the denominator, it's always going to be opposite quadrants. So this is a pretty good graph. The only point I have not considered is that point, and I shouldn't really circle it. It makes it look like a hole. How would I figure out what that point is?
Plug in 0 for x.
Correct. And you get minus 5/3. So that point right there is minus 5/3. And I can plug it into either the original function or the modified function. The only difference between my modified function and the original function is I have to include that domain restriction, that x cannot be equal to minus 4. Because if I look at just the modified function, I don't see that. I don't see any domain restriction where x can't be equal to minus 4. That only comes from the original function.
Okay.
Okay? And I think we're doing everything they called for. Let me look at those instructions just a little bit better. Sketch the graph. As sketching aids, check for intercepts, vertical asymptotes, horizontal. Yeah, that's exactly what we're doing. Okay. Good. Which one next?
26.
Okay. I'll go ahead and write it as stated. That's my first step.
And then the top is x plus 4, x minus 4. And then cross out x minus 4, and then there's a hole at 4.
So I'm left with just x plus 4. Now I graph that. You see how I'm left with just x plus 4?
Yeah.
Okay. How do you graph x plus 4? It's the y-intercept.
4.
It's the
And then
slope.
it's
It's the slope.
1.
1, exactly. A lot of people, when you don't write that 1 in front, like you're not supposed to, they don't see it. And they don't realize, you can't believe how many people answer that question x. But it's not x. The slope is 1. So I got to go up 1 and to the right 1. And there's my line. Tried to make it go through those 2 points. Wasn't terribly successful. And I still have to put my hole in there. And that's what it looks like. Here, I got some other marks in there. Let me erase. Whoops. Now, if you were to graph that on either Wolfram Alpha or your calculator, you're not going to see that hole. Not going to show. It's going to be a solid line. That's because it's so tiny that the graph calculator can't show it. It doesn't have the resolution. Remember, that hole is at 1 point only, at 4. No other place. So in reality, it really is infinitesimally small and wouldn't show up. And when you're graphing it manually, you draw it in like that just to show that x cannot be equal to 4. And that's its only restriction. The domain is all real numbers except x cannot be equal to 4.
Okay.
Okay, what else?
43.
Okay. So the same, okay. Not quite the same because it uses a slant asymptote. Notice what's different about 43 is the numerator, the highest degree in the numerator of the variable is exactly 1 greater than the denominator. It's a 2 versus a 1. When you have that, you have to do the division. That's the first step. In other words, divide x into 2x squared plus 1. Well, I don't actually need to do this long division because I have a single denominator, so I can do that division just by splitting this up into 2 fractions, right? In other words, this is this fraction plus that fraction. So what I really have as a function is 2x plus 1 over x. That's my function. Okay? And this is a remainder, so the slant asymptote goes there. Yeah, is 2x. The equation of the slant asymptote is 2x. Well, that goes through the origin, has a slope of 2 on it. Whoops, let me draw it as a dotted line. All right. Now the question is do we have any other asymptotes?
No.
Is there anything x cannot be? Look at the original function.
It can't be, wait.
Can't be 0. In fact, you don't have to look at the original function. You can look at the function that I changed it into, and x still cannot be 0.
1 cannot be divided by 0.
Right. So we do have a vertical asymptote at x equals 0. Okay, we figured out our horizontal asymptote. Here, let me write this in a little nicer way. This is equal to 2x plus 1 over x. But we do have a vertical asymptote right there. Okay? And there's no horizontal asymptote, as we discovered last time. I wasn't sure, but I am now. So we have to graph our hyperbola, and it's going to look like one of 2 pictures. It's going to look like this, or it's going to look like this. You see how I could get either one of those?
Yeah.
In other words, the only thing that matters is that the function approach the asymptotes. And both of those do. So we have to figure out which one to pick. Now that's a little harder on this because we're dealing with a slant asymptote. But if we pick x equals 1, let's call that 1 right there, then the function should be at 3, right?
Yes.
That looks to me like the red, not the green.
Yeah.
Okay, so let's erase the green. We don't always have to draw both of them. I just do that for kind of instructional purposes. And you can see that if I made x 10,
It would be 10 and a 10th.
well, it would be 2 times 10, 20 plus a tenth, so it would be 20 and a tenth, and that's making x 10. So it would be up there. My red still looks correct.
Yeah.
Now, notice that it's not a terribly easy thing to do to figure out whether I'm using my red or my green. One way I could realize for sure is if my red is correct, I don't have any x-intercepts, right?
Mm-hmm.
If my green was correct, I would have had an x-intercept, right?
Yeah.
Okay, well, let's figure out if there's any x-intercepts to this function. Well, x-intercepts means y, or f of x, is 0. So I'm going to substitute 0 and see if I can find a solution to that. Is there any way that can be 0?
No, because
The numerator has to be 0 for that to be 0, and that numerator is always a positive number. No matter what x is, if you square it and add 1 to it, you get a positive number. So that tells me I do not have any x-intercepts and guarantees me that my red function is the correct one.
okay,
Now,
I understand.
where is this point right there? Believe it or not, without calculus, you can't tell.
Yeah, I don't know.
The way we figure that out, in other words, if they said, what's the range of this function, you'd need to know that point, and you would need to know this point here, right?
Mm-hmm.
I wouldn't be able to give you a range otherwise. I could give you a domain. The domain is all real numbers except x can't be 0. But the range is much more difficult to give you, and in fact, the only way you're getting a range is to graph this thing in your calculator, look for local mins and maxes, and put your trace on either side of that little valley there, and it'll tell you what the y value is right there. And it'll tell you what the y value is right there, and then you'd be able to state the range. Now, it doesn't ask you to do any of that. It asks you to just graph it, but part of graphing it is knowing where that number is right there. In other words, I graphed it approximately, but I didn't graph it exact because I don't know what the y value is. I have no way of figuring it out. I don't know what the x value is right there.
Mm-hmm.
But a graph would tell you.
Okay.
I don't know if Wolfram Alpha, I guess Wolfram Alpha might not. Yeah, because it's going to give you the range. So it would give you the values. But because Wolfram Alpha doesn't give you a trace that you can stick on the curve and find out where that value is. All right.
I have a question. I was wondering what the, wait 1 second. It's like a, let me find it really fast. What's the rational zero theorem?
Okay. Rational zero theorem says that if you take a polynomial and if I want to know how to factor that, let's say that you tell me one of the factors is 5. One of the zeros is 5. If that is a true statement, then when I divide this polynomial by x minus 5, I must get 0 remainder.
Okay.
If I do not, then this is not a factor.
Okay.
And that's what the rational factor theorem is. In other words, once you come up with all your possible zeros and you start checking to see whether they really are zeros or not, you do synthetic division. Remember that last step in synthetic division is if you get a 0 in that box, it is a 0, and if you get any number other than a 0, it's not a factor.
Okay.
So
what's
all of your factors of this polynomial must produce a 0 remainder when you divide the polynomial by the factor. That's how you can tell whether it's a factor or not. is by dividing it. Whether you do it synthetically or by longhand doesn't matter, but synthetic is the easiest way to do it. And you either produce that 0 or you don't, and that tells you whether it's a factor or not.
What if you're not given one of the factors?
Well, then you have to use the rational factor theorem, which is a little different than the 0 factor theorem. The rational factor, if they don't give you a factor of that, now I just made this polynomial up, so I'm not sure that there are any rational factors, but if there are, it would come out as P over Q, and P has to be a factor of the constant, and Q has to be a factor of the coefficient of the highest term. So in this case, possible P's are plus or minus 10, plus or minus 1, plus or minus 5, and plus or minus 2. Possible Q's, plus or minus 3, plus or minus 1. Now, what are possible rational factors? You have to take all combinations. In other words, you have to look at the 10 over the 3, the 1 over the 3, the 5 over the 3, the 2 over the 3. And you have to look at the 10 over the 1 over the 1, 5 over the 1, 2 over the 1. Those are all your possibilities. In other words, 16 possibilities. There are 16 possible rational factors. And the only way to find out if one is to pick one and start doing your synthetic division until you produce that 0. Remember, we did one like that. Only we didn't do a complicated one. When we met in person, we did one that had like a 3 as the number, and the coefficient was 1. So there weren't a lot of possibilities. I made this one up merely to illustrate this P over Q concept.
Okay.
And the fact that when you have two different numbers in the denominator, you have to take all combinations. In other words, you have to check 10/3, you have to check 1/3, you have to check 5/3, you have to check 2/3. And you also have to check 10 over 1, 1 over 1, 5 over 1, and 2 over 1. Both positive and negative of each one. It is a nightmare to do these.
Yeah,
If you have to do them this way, it's truly you're only going to get one of these on a test because they take so long. If they gave you 2 of them, that'd be the whole test.
yeah, that would.
So there's really 2 theorems that apply when you're trying to factor a 3rd degree or higher polynomial. And that is the rational factor theorem, which is the P over Q, and the other is the zero remainder theorem, which says that if one of these numbers is indeed a factor or a 0, then when you divide it into that, you will produce a 0 remainder.
Okay.
Okay. Stacy, you good to go?
Yes.
Okay. I will talk. And you got the link to the video?
Yes, I did.
The other one, so you know how that works. Okay, cool. And I won't send you that link each time. Is all you need to do is go to that channel and look for your file, the one that has your initials SL.
Okay.
Okay, and the right date.
Okay.
All right.
Thank you so much.
You're welcome. I will talk to you next time.
Okay. Goodbye.